All right, let's jump right into this explainer and unpack the foundational tools that every software engineer absolutely needs in their developer's toolkit: core data structures. Now, this isn't just about cramming to pass some technical exam. It's about really understanding the underlying building blocks of the software we use every single day and learning how to make our code faster, cleaner, and just significantly more efficient.
We've got a fantastic roadmap for today. We're going to cover arrays and matrices, linked lists, stacks and queues, JSON and parsing metrics, and then we'll put it all together with a dry run challenge. Starting right off with Section 1, Arrays and Memory Matrices. So the absolute most fundamental tool we have is the array. Elements are stored in contiguous, side-by-side memory blocks, which gives us instant access, assuming we know the index, of course. But when we expand that into two-dimensional memory matrices, there's a pretty stark contrast in how the data is actually stored behind the scenes. We've got row major order, where data is packed row by row, versus column major order, which packs it column by column. Knowing exactly which one your system uses is totally essential if you want to optimize memory speed. And what about when we actually manipulate those matrices in practice? Say you need to perform an in-place 90-degree clockwise rotation. Honestly, don't overcomplicate the math here. It is just a super elegant two-step process. You transpose the matrix by swapping your rows and columns, and then you just reverse each individual row. Quick word of caution, though. You know the old joke that the two hardest things in programming are naming variables and off-by-one errors? Well, you are completely in the danger zone for those off-by-one errors during matrix rotations and nested loops. Always, always double-check your loop boundaries, or you are going to crash your program. Moving right along to Section 2, the linked list structure. So if we abandon contiguous memory entirely, we gain massive flexibility. But there's a direct trade-off. A singly linked list gives you incredibly efficient forward traversal, but you can only go in one direction. Now, a doubly linked list solves this by throwing in a previous pointer, giving you bidirectional freedom. The catch? That freedom literally doubles your pointer memory overhead. You've got to decide if that cost is worth it for your specific build. Now here is a really clever variation. If you take the tail of the list and connect it right back to the head, you get a circular linked list. And this isn't just some abstract theory. This is the exact mechanism keeping the computer you're using right now running smoothly. It's heavily relied upon in round-robin CPU scheduling to just endlessly cycle through active tasks. Okay, listen up, because this is a massive danger zone when you're dealing with pointers. If you want to delete a node, let's call it node X, you absolutely have to bridge the memory gap to the next element before you free X from memory. If you free X first, boom, you just severed your entire list and tossed all the remaining data right into the void. All right, Section 3, stacks, queues, and rules. We're moving from flexible lists to restricted access structures that have strictly enforced rules. First up is the stack. Just think of a stack exactly like a sleeve of tennis balls or those stacks of plates in a cafeteria. It strictly follows LIFO, last in, first out. The last item you push onto the stack is always the very first one you have to pop out. On the flip side, we have the queue, which operates completely differently. It works exactly like a line at a busy coffee shop, adhering strictly to FIFO, first in, first out. You enqueue at the rear and you dequeue from the front. The first element to get in line is always the first one served. Now, when you're using arrays to build these stacks, you've got to safeguard against state anomalies. You'll hit an overflow error if you try pushing a new element onto a stack that's already hit its maximum capacity. Conversely, you're going to trigger an underflow if you try popping from a completely empty stack, which, by the way, you can easily track when your top index equals -1. But queues have their own fatal flaw when built on arrays: the linear queue problem. As you dequeue elements from the front of the line to process them, you create permanently unusable dead space at the front of your memory block. It's kind of like a line at a theme park where people just refuse to step forward after the person in front gets on the ride. The line moves, but that old space is locked away forever. So, what's the brilliant fix for this dead space? The circular queue. To reuse that empty space at the front, the system uses modulo arithmetic. Basically, it's math that makes your memory index loop like a clock, wrapping the pointers right back around to the beginning. It completely solves the problem by creating a continuous, highly efficient loop. Next up, Section 4, JSON and parsing metrics. So, with our primary structures mapped out, let's take a look at how modern systems actually package all this data for network transmission. You see this format literally everywhere: JSON.
It standardizes our configurations into a super lightweight, readable collection of nested key value pairs, all neatly enclosed in curly brackets. And because values can be strings, numbers, arrays, or even other nested objects, it is universally adaptable.
But, and this is important, mapping those string tokens into actual memory scales at O of n space and time relative to the payload length. This is a parsing metric that comes up all the time in modern exams, and it matters. Because while JSON is incredibly lightweight to read, processing massive payloads can unexpectedly bottleneck your CPU and memory. It simply takes linear time to churn through it.
Okay, let's bring it all home with Section 5, the Dry Run Challenge.
It's time to actually put these concepts to the ultimate test and trace the mechanics step by step. Here is our scenario. We are allocating an empty stack S and an empty circular QQ, which has a maximum capacity of 4. We also have a variable, x. We need to track their exact memory states. Let's kick things off with the first 3 steps. We push 10 and 20 onto the stack, so our top is now 20, but immediately we pop that 20 right back off and enqueue it straight into our queue, Q. That leaves our stack with just the number 10, while our queue now holds 20 at the front. Moving right along to steps 4 through 6, we push 30 onto the stack. Next, we peek at it. Remember, peeking reads the value without actually removing it. So we take that 30 and we enqueue it into Q. Finally, we enqueue 40. We are rapidly filling up that queue's capacity. Our stack is now sitting at 10 and 30, and our queue holds 20, 30, and 40. And for the grand finale in step 7, dequeuing from the front of Q takes the oldest element, which is 20, and assigns it to variable x. This perfectly finalizes our ledger. Stack S finishes at 10 and 30, QQ wraps up with 30 and 40, and variable x is proudly holding the value 20. Nailed it. Now that we've totally mastered this toolkit and conquered the dry run, I have to ask, based on everything we explored today, would you like to jump straight into hierarchical data like binary trees next? Or do you want to tackle some trickier, advanced variations of the linear structures we just learned? Think about where your curiosities lie, and let's keep building that toolkit.